world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute.
Said that there's that dual pole is a fact, though, so I've never said that. I've said specifically I've never mapped the whole Earth, which none of us have, so wouldn't be expected any of us would have any independent mapping of the Earth unless you've done so, or unless anyone's done so.
Yeah.
All
And I
right,
can't
lads,
imagine there's a
we
how.
are ready for our celestial theodolite update here. All right, lads. So to kick us off here, we got to do an update / retraction from last week on the preliminary, excuse me, on the preliminary analysis from Shane on the plane data. If you do the star position minus the globe predicted geometric peak, you make the, that's not what the globe, how they would predict it. You have to include or you have to subtract the central angle first to get back to the observer location, and then subtract the geometric peak angle, which gives you the difference in the way that the globe lads would prefer predicting from the observer location. So sincerest apologies for that. We will be, but that also goes into, or like that same situation though ties into the subject matter of today too. So it all works itself out there. So when we look at these occlusion timings, we see here that flat Earth predicts a time that's later than what the globe Earth predicts, and we're gonna illustrate why that is. So real quick, if we look at the plane data, so retraction on the plane data, doing it from that position wasn't how the globe would predict it. So when you do it correctly through analyzing what flat Earth predicts at the end of the arc length using the plane location versus the observer location, the globe matches closer in, I think, every scenario. And when you look at the geometric intersections here, you're going to see the timing difference for flat Earth and globe Earth. Globe Earth is still earlier, so the globe lads have been saying, well, it works geometrically for the plane angle because XYZ, but they still end up with what would be an earlier timing. So for the purposes of today, and this is a highly contested issue and an extremely important one to the celestial theodolite and data analysis. So today I really want to focus in on honing in on the why this is an earlier time versus what flat Earth predicts using the Stellarium software and whatnot. So we will go through all of these, and then we'll take some questions at the end. And like I said, I'll only have an hour tonight, so we'll kind of keep it to this specific subject for the night. Okay. I think that is everything I wanted to start with. Brian, I think whenever you're ready, sir. Brian put together a little presentation / simulation to show the geometric implications of why the globe predicts the earlier timing. So Brian, whenever you're ready, good sir, can you hit the screen share?
I don't have permission.
All right. How do I give this man's permissions? Let's see. I think Gio will help out with that here in a second. Waiting for tech support. Yeah, I don't know how to give you a rank in here. It's not coming up. I don't have permission. So, yo, Gio, are you there?
Or Jeremy or any other moderator.
Yeah, Ernie or Jeremy. Jeremy! Jeremy! Well, that's crazy unfortunate.
Hey, Andrew, do you know if you can do it? I don't know if I can do it from my phone. Is that Lamazing?
That's correct.
I'll try my best, but I couldn't even do this for myself the other day. That's a showstopper. I don't know. Is
Yeah,
there any way we can proceed forward and come back around when maybe one of the other fellas show up?
yeah, it was kind of dependent on his simulation though, but I can kind of show from Stellarium while we're waiting, I suppose. So move this over here. Okay. So for the example of Pikes Peak, actually, give me 1 second. Let me grab some water. All right. So for the example of Pikes Peak here, we go to the occlusion time, which is 1843:07 observer location. And we see the star here is at, oh, no, this is at the peak, sorry. We go to the observer location. Thank you, Lev. And we see that the occlusion, we see that the angle here is 206. So 2 degrees and 6 arc minutes. So if we go back in time by 2 minutes and 29 seconds to 42:04, we see that the star would have been at 217, which is with the geometric angle that the globe predicts. So it had to get, it already intersected with it at that time. Now the reason that that this occurs like this is that the globe is always moving the star positions to compare it to where an observer would see it at the center of Earth. So to linearize their 60 nautical mile per degree rate and to maintain that for the drop rate, the comparison for the stars is always done with respect to that observer, and that of course always lowers the star, the star's true position relative to what the observer actually sees for the apparent position. So when you take these different angles, like in 10-degree increments, and you remove the refraction level, you're comparing that, what the calculated true position would be with respect to that fictitious observer, and it's always lower for the lat on the globe. And in doing that, that's what creates the terrestrial curvature as well. So they're following the same thing 1-to-1. So if a mountain peak is lowered at the horizon by 13 arc minutes, well, then your perception of the sky is lowered by 13 arc minutes. So when this star, if we were to go back to, let's see, what time would that be? When it's at 2:33, 2:28, 29. 1 second.
Looks like I'm good now, Alan, by the way.
Okay, cool. We'll get you here in a second. So what was it? 2:30, no, 2:33. We got to go to where the star's true position was, 2:33:22. So if you rewind by 27 arc minutes for the observer starting position, you get this position where it would be at the star. Now, some people would say, Alan, how come you're not predicting flat Earth from the observer location? Well, we can't do that because this is all starting with a curved baseline for not only the sky, but for the ground. So the star's position, if we're going to compare it from observer location, is comparing it to what the globe angle would predict. So in other words, this 233 angle and then waiting until it intersects at 231 isn't the correct location to predict for flat Earth using software that already has a curved baseline. Now, when we change positions to the mountain peak and do the comparison, that's when we're flattening that baseline and comparing where the star's position is at the time of occlusion, and that elevation difference or alignment to the peak with respect to the star will determine whether or not that baseline is flat in reality or if it's curved. And then we can get into the geometric formulas and stuff for why, but to just kind of keep it simple, the globe is always comparing to the observer at the center of Earth, and it's and that's why that works out that way. So when you advance this by 2 minutes and 29 seconds there, you should get 204. Yeah, you should get the alignment for the geometric peak for the observer. And then if you go to the peak, you'll see that the alignment, like let's say the occlusion happened at this time, closer to what the globe predicts. If we then flatten the arc length and check at the peak what the position of the star is minus the rise over run, we would be at 2 degrees and 44 arc minutes. So we would be about 13 arc minutes over the elevation of what we predicted for the rise over run, because we failed to account for the fact that the elevation difference between us is dropped by 200 meters. So that's how it would determine that we were off on that. Now, when we get into the refracted position, that's just adding the time from the drop over distance back. So we see that if for 13 arc minutes of drop, it takes 1 minute and 15 seconds for a star to drop that much angularly, but they also add back that same amount in refraction. So it ends up making it so that the star lingers long enough to meet the flat Earth prediction, where it goes across the full arc length rather than only half of it. So with that said, we can bring up Brian's screen share now, and he can show us what he made to represent that scenario as well. All right, Brian, whenever you're ready. Oh, let me stop my screen share, and then everyone please join Brian's screen share, the amazing up there.
Okay, so I've got a Desmos simulation here that's will illustrate the difference between the flat Earth model and the globe model, and then explain why the time is earlier on the globe. So you can see here, I've got a green line for the flat Earth, and a pink line is the profile for the globe. And this is Pike's Peak from observer to the peak. So on the flat Earth, the sea level line would be the x-axis, and then the globe is this blue circle, with radius of the Earth. And then the central angle on the globe starts at the center of the Earth. I guess I should explain the black circle is the celestial sphere. So the central angle goes from the center to the observer, and then to the globe peak. The amount is 27 arc minutes. And I want to show the half gamma here, which is the dashed line here. I have a nice visual to show what Alan's always talking about here. So first, I'm going to rotate the angle 90 degrees, and then slide it up to the peak. So you can see it's intersecting the globe peak, and then if you go half the gamma angle, 13 arc minutes, you get to the prediction for flat Earth, which is 200 meters higher. And then you can also see, if you look directly below, there's 200 meters of drop between where the flat Earth and globe. And then if we so this all goes back to the null hypothesis. So we have a different geometry that's mutually exclusive between the globe and the flat Earth, and then we can test it to see which is a better match to reality. We have Earth is flat or it's not flat. It has to be one, and it can't be both. So what we can do is we can take the true star angle from the peak at the time of the occlusion and plot it on both models. And usually we do the peak on the flat Earth and from the observer on the globe, but I think that confuses people about why the time's later, so I'm going to actually do them both from the peak, so then you don't have to convert, and then you're comparing apples to apples. So here is the star true peak angle plotted, and this is actually the same angle for both. It's the angle to the star from the peak at the time of the occlusion, but notice the dash green and dash pink are not parallel. And that's because eye level for the observer on the flat Earth at the peak is different than it is for the globe. Flat Earth matches the observer's eye level, and on the globe, you can see it about lines up with the 4100, and then it drops half a degree on this side. So that's the gamma difference. They're different by an angle of gamma, the central angle. And then another important consideration here is that the stars on both models are not in the same location. So you have the celestial sphere is this black line, and the globe predicts it drops at 15 degrees per hour. So as time advances, these stars would go clockwise. But the flat Earth model has a lingering effect built in, and that difference is going to be the gamma angle. So you can see 233 minus 25, that gives you your 27 arc minutes for the central angle. And the difference between the star positions is important. You can see on this plot, you've got the blue line represents a celestial sphere where the globe predicts the stars are. But in reality, the stars appear at these orange dots. There's a lingering effect. And that's explained on the flat Earth model because the stars are actually moving away, and it would make an asymptote where they never actually go below the ground.
So instead of continuing that linear rate to, to complete their cycle, it would just, linger at the horizon and not really go to a certain point where it goes below you. It's just going to kind of be stationary in the sky as it moves away.
Right.
Any explanation for that lingering effect and why it doesn't apply to other observers of that star?
Please save questions to the end. I don't want to lose my train of thought here. So then, go back to the null hypothesis. We can take that true star angle and put it from the observer. So if the Earth is not flat, then you wouldn't expect it to line up with the flat geometry, as you can see it does here. So that's a problem for the globe. The null hypothesis is not refuted. And then if we go back to the true peak, to the angles, star true angles plotted from the peaks, what we do is we line them back up to the observer and see what the alignment looks like. So you can see the flat Earth misses the observer by about 30 meters, and the globe has 170 meters too high. So the globe would then have to invoke 170 meters of refraction to bend the light down to meet the observer. And then, so the time of the occlusion is 1843.08. If we move it forward by 11 seconds, you can see flat Earth lines up. And if we go back a minute 4, then the globe Earth is in alignment. And that's really all there is to it. Any questions? Des, I guess we can start with you. Can you state your question again?
Yeah, so you describe this lingering effect. Do you have any potential causal effect? And secondly, if we add a second observer into your geometry, why do they have a complete...
Okay, let's do one question at a time, please.
Okay. Yep.
So just think of an airplane flying overhead, right? You're going to see it. It's just a matter of optics and perspective. The airplane's eventually going to merge. If it's flying away from you, it's flying straight and level, but it's eventually going to appear to merge into the horizon, right? But it's never actually going below the horizon. Well, I guess it's, if you assume there is flat. If you assume it's a globe, you do assume it's going below the horizon. But that's just the way we see. It's a nature of our vision.
Okay, so I'll give you that for now then, knowing that if we measure the position of the plane, the angle to the plane, it's...
airplane, let's clarify, right, versus like mathematical plane.
Yeah. So the angle to the airplane from the observer doesn't exhibit that behavior, but we'll leave that for now. So the second question is, if I have another observer, where do I put him in your diagram? And how do I give a coherent solution for both observers simultaneously?
Both observers seeing the star?
Yeah. So both you have so ultimately the occlusion becomes irrelevant. It's the position of the star at the time, right?
I understand what you're saying.
If we have another observer somewhere else, why do they get a different angle to the star? And
So Alan calls the star position the true star position, but it's still actually an optical effect. The star would actually be coplanar to the ground, and then it's curved onto the celestial sphere because of the nature of how we see. So the position mapped to the celestial sphere would be different for two different observers. And as they advance their distance, it's going to move relative to each observer.
Okay, but you have no physical explanation for that.
Physical explanation for how we see?
No, for why the measured position of the star will be different for two observers through the same physical atmosphere.
That's just the curved nature of our vision, how we see.
No, we're measuring these things, right? Our vision doesn't come into play here at all. It's a optics.
That's literally how we get the occlusion time. It's an observed
Yeah,
observation.
but we
with our
don't need to
eyeballs.
use.
So
our perception
basically,
to measure it, right?
if there's stars in the sky and observers see them at different angles, it's because the Earth's a globe, not because of optical phenomenon, right? That's basically what you're saying?
Well, if you can come up with a coherent optical phenomenon that explains it simultaneously for everybody, that would be cool. So the other related question to this is, so we have our occlusion. So we've got the observer, Mr. Heffron, looking at the Pikes Peak.
So before you move on to your next question, though, did you understand that Brian answered your question? The answer is just how
Well,
you perceive it.
he
And we all
answered
have
it,
our
but he didn't
we
give
have
me
our
a
own.
satisfactory answer.
Oh, well, not satisfactory answer isn't the same as didn't answer it, because the answer is just how every observer perceives it. They're going to see it at different angles relative to where
So
they're
just
at. Yo,
give
no,
every observer
no,
their
no,
own
no,
set
no,
of
no,
physics. That's cool.
real quick. And then your contention was, yeah, but nah, it's a globe for sure. Just going off of how it's optically perceived and not going off of any sort of geometric measurement from the occlusion. Your question is about trying to make it so that, if you see a star at a different angle, therefore a globe. Like it's not a real argument, dude. So what's your next question?
So the next question is, there's some hypotheticals here, so you'll have to deal with me. So we'll just transplant our observation to the equator, and we're looking west. So we're observing. So our 15 degrees per hour is directly downwards, right? So nice click, 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 linear, 15 degrees per hour. So we have our observer, we have our occlusion time and angle. And nominally in your diagram, there's a line, right, between the observer, the peak, and the star. We can create that occlusion anywhere along that line with another object, right? So I could stand up a pole 100 meters down the road and generate the identical occlusion to the mountain. It will have the same time, it will have the same angle. But your methodology, so if I did it 100 meters down the road and the mountain's 70 miles away, your methodology would give the occlusion time to be 4 minutes earlier, because it's about a degree, right?
No, that's incorrect. You got to remember that the true star occlusion angle comes from the location that's where it's doing the occlusion. So
Yeah,
if you have a pole that's really close, it's going to be close to the observer. That's a small gamma. If it's a mountain that's far away, it's a large gamma. So the angles are different by basically gamma. The central angle.
So the angle at the base of the triangle formed by the occlusion is not our angle.
Our being the globe model?
No. So in the diagrams that you guys circulate, you have the observer, you have the mountain peak, and a line from the observer through the mountain peak. So that base of the mountain, observer, star angle, so the angle at the observer, that also corresponds to the angle at the mountain. Is that my understanding of your model?
If
Pretty
you
much,
add the
yes.
if you add the arc length
Okay,
back, yeah.
So if I make the occlusion happen 100 meters away from me at the same time and the same angle, why can't
It's
I
not at the
then?
same angle.
Yeah,
No, they will be.
it would be two different distances. No, you can't merge them together
They're
just
different
because you're over.
distances, but the occlusion angle is the same and the
Yo,
occlusion time is the same.
and it's based off of two different distances.
So
It's
why
two,
does the
it's two,
distance
it's two
impact
separate,
this
it's
then?
two separate comparisons.
It's the same model, right? Your model
You're
doesn't
you're
specify
using
where the
two
occlusion
things
needs to
at two
happen to
different
work.
distances to occlude. It's two separate analysis.
Oh, okay, I understand the question. And the reason is because of the height difference. There's also a factor of height, which Stellarium does not model correctly. So it's really the height of the where you take the peak that also affects it.
I don't think the stellarium height will alter the observer's angle very much, will it?
It doesn't at all, but it should,
Why should it?
for the reason you just stated.
But if you have it's quite confusing as to where the star actually is in your model. But so
Well, first of all, the model that we're using is the celestial sphere. So wherever the observer's at and whatever time it is, that's where the true position is said to be for the reference. We're not using a custom model or a different reference point. So it's not confusing to determine where it's at. It's your own model.
So our model, the globe model, if I move if I take stellarium 100 meters away for the same occlusion time and occlusion angle, it will give me a significantly different angle to the one that you get at the peak. And if I were to...
That's not true if you add in refraction. It would basically match what the flat Earth predicts if you do that.
So what is the role of refraction in this model?
The globe Earth needs refraction to make it the globe Earth fit what we see in reality. And it's just a correction factor.
And on that real quick, when we talked about the spherical integration from the recent scripts that have been coming out to do the ray tracing and whatnot, the air density from standard sea level, or mean sea level, is already baked into it as the assumed refractivity to air density relationship. So any real world values that deviate from that are going to add plus or minus a little bit to it. But if you don't add anything, if you don't add any real world data to it, and you just use the mean sea level values of 15 degrees Celsius and whatever the average temperature or pressure is at mean sea level, I think it's like 1,000 or something or whatever. But when you put that in, it changes the refraction at Pike's Peak from 19 arc minutes using real world values to 21 arc minutes. So it doesn't impact it that much. It's already curve fit as the air density refractivity proportionality model and curve fitting to the radius. So what we're saying is that the curve or the correction as refraction that's applied, you would never know if it's actual refraction or if it's been geometrically curve fit, because the actual refraction conditions are only 2 arc minutes of refraction with temperature and pressure, but the spherical integration is what gives the extra 11 arc minutes.
Yeah, but that's the good thing about the integration, right? So integrating and getting...
That's the good thing about the input being the globe and the output is the globe. That's circular. That's not the good thing about it, bro.
The refraction model works concurrently for every observer and every celestial object, right? So there is only one physical model, and that same integration through the same physical model gives the same results that match the observed results, right?
It makes...
So the fact that you're just picking one integration, it doesn't account for the fact that every other integration you do also works.
Well, first of all, you're saying different integrations, like there's different ones. There's actually an international standard that's set and they all use the same one. That's why when Astronomy Live did his and when Ruhif did his, and they all use the same refractivity value that came from the 1930s as per the curve fitting, and then starting from Willis and then Garfinkel, which we've already been through. Now, you're saying that the fact that it matches all observations is a good thing. However, you're disregarding that the input to start the integration was the radius of Earth, assuming the globe, and then assuming spherical symmetry for Snell's law for it to make concentric shells around us. So everything in the model is assumed to be, is assumed that the radius of Earth is why is the justification for the integration. But you can't tell now, based on observation, if the integration is correct or if it's just curve fitting, because it already curve fit. It already did that. It can't produce a different result. Everything is going to be baked in as a baseline for Earth's radius. That's why when you don't input anything, it already covers all arc lengths. So,
yeah. So I
if I
partially
can
agree
interject,
there
I just posted the Desmos in the chat if anyone wants it.
So I partially agree with you there, Alan, in that the curvature of the Earth and the curvature of those refractive layers is important in the end result. But we can actually, and I assume you've seen Ruhif's latest video, and he went
Yeah.
through and collected real data and
Yeah, he did this.
calculated.
He did the same thing. Look at his air
Yeah,
density
yeah.
values. You say, yeah, but then do you not understand what you're even saying? He used the same air
So
density values as everyone else did.
Yeah, so he used real physical collected
Yes.
data to
Yeah.
build his model, right?
No,
And
he used temperature and pressure, and then used the air density value derived from 1913 over spherical integration.
No. The
Yeah.
density value doesn't involve any integration, right? That's the
No, it's literally the driving force of it.
Yeah. So, but if you
So you're saying no, and then yeah, bro. Like you're just saying random things, and I can't stand it. It's in his source code. You're like, just go pull up his source code and look at the air density value. Right? That's all you need to know.
There are two things happening here. So one is
Daza.
Temperature, pressure to density, so that you can do the refractive index of air at that position.
Daza.
Then there's the gradient. And then you have to integrate or ray trace across that gradient to get the curve and the angles, right?
Nope. So what we just started with was the air density. You put in temperature and pressure, and it adjusts that baseline, plus or minus a little bit. If you just put in nothing, it still already curve fits to everything. It doesn't matter. The input is the globe. The output is the globe. You can't get around it. What Ruhif did was the same thing that everyone else did. It's nothing different. When you say he put in real world values, he put in temperature and pressure using the air density value to make the refractivity proportional to the air density. That's the spherical integration of it. That's what makes it work over any arc length. When you integrate it over the angles and whatnot, that's just ray tracing it out for the spherical symmetry to turn 2 arc minutes into 13. Nobody can know for certain if the 13 arc minutes is real or not, or if it's just a geometric correction to what it has to be over that arc length.
So I have a fundamentally different understanding, and I assume we're talking about the Ruhif's video from like last week.
Have you hold on a second? Have you looked at Ruhif's source code? Forget the video. Have you looked at his source code?
Yes, I have. Yeah.
Okay.
Yeah,
so can you do me a favor? Can you do me a favor and just Control F where you find air density?
I haven't got it open now.
That's all that needs to be discussed.
We're really deviating from the topic here, and I wasn't planning on sticking around long. Are there any other questions related to why it's an earlier time on the globe Earth?
Well, I was gonna ask about that at some point.
Go ahead. Now's the time.
So, well, first of all, do you guys, from keeping up with it and from the earlier presentations, it seems like you guys didn't say in your presentations that the occlusion was later on the flat Earth, correct?
On the early prezzies,
there's a caveat here, and for occlusions where the star is set behind the mountain, it is later on a flat Earth. For immersions where they look the other direction and they rise, then it's earlier on a flat Earth. So it depends on if it's an occlusion or immersion.
Yeah.
Occlusion, dude.
Yeah, but to answer your question though, QOP, yeah, for the first couple, I did definitely say it in that way. And then when we added the timing calculations to the spreadsheet where you could see the timing differences, I noticed that they were different. And then I started looking into like why and all that. And then that's when we realized why we predict from the peak and all that and stuff. So
it sounds pretty ad hoc.
Well, it sounds ad hoc, but it's geometry. That's what I was going over with you last week when we were going over the chord tangent stuff. That's why we do it, because their baseline. 1 second, please, because their baseline's already curved. Go ahead.
So to simplify it for everyone else, it seems like what you've done is first you guys claim the geometry of the curvature would have the globe have the occlusion later, and now you guys are saying don't worry about that. The sky on the flat Earth behaves differently and would have a delay with the occlusion, causing it to occlude later because of like flat Earth, perspective, having the star kind of disappear in the distance, kind of thing.
Yeah, that's exactly it. So when we went through the central angle stuff and the chord tangent theorem, the reason that Mike was moving to the peak to look at the star position is because the globe starts with that curved baseline. So the angles that you get from it from observer location aren't the correct way to interpret it for a flat Earth. You'd have to go to the end of the arc length and then see where the star is at, and the elevation difference between the two is going to be, essentially the same amount of curvature as the amount of drop over distance predicted over that. So, not fully understanding that as we started understanding more and stuff, we refined the argument to what it actually is.
So I don't completely disagree with that, but it's obviously not what happens all the time, right? I've never seen a sun fade out where the sun gets smaller in angular size. It seems like usually we have this hemisphere that behaves like the glober's claim. So that's why how they reverse engineered the globe out of what we see, is because usually we see things pretty much drop around a hemisphere and not this, what you would assume, like obviously, like if you saw like a sun fade out and kind of like get smaller and go into the distance, no one would have ever been able to been sold the globe. So that obviously I mean, it might happen sometimes. I've never seen it.
So the radius of the celestial sphere is 6 million meters, and you can't see the sun that far away. So that's why it doesn't appear that way most of the time. If you had like infrared, I'm sure you could see it.
Yeah, I got infrared. I might try that. But yeah, so obviously it does, like, it changes, right? Sometimes atmosphere cuts off, and makes things just drop down straight, like around the hemisphere, and then sometimes it makes things like fade out a little bit more delayed. So
Well, just
the
look at
fact
your
that you
weather
guys are
app.
having
Just look at your
fact that
weather
you
app.
guys
If it
are
says the visual visibility is 7 miles, that's as far as you're going to see.
well, what I'm saying is, like, you guys are claiming to get a consistent occlusion that's happening later than what Stellarium suggests.
Yeah.
Um, but
For
what we
every
see, what you guys are contributing to that doesn't happen like all the time. It usually doesn't happen.
happens every time. So you can go through the data and look at it. It happens every time.
Well, the occlusion happens later, what you guys are apparently finding, which I haven't gone through all the data. Um, that's not proof of what you're saying is causing it, right? So that's circular.
You
I
got to
don't.
go back to the null hypothesis, and that's all
Yeah.
about the null hypothesis. You refute the null hypothesis.
That's not really.
So the thing is regardless of what mechanism we say causes it on a flat Earth or what have you, like, we hypothesize that it's optical phenomenon, right? But regardless of what happens, geometrically, there's a specific thing that's supposed to occur per the chord tangent theorem and all the stuff that Euclid did that we've been going over. And when we do the analysis at the occlusion, when the star is occluded, it never adds up to what the globe geometrically predicts, only what flat Earth optically predicts. Now, or geometrically. So the reason for that is because the star on flat Earth, right, is like moving above us. We're just perceiving it get lower. But when it gets to a certain angle, because it's not actually because the reason it's getting lower isn't actually dictated by being on a ball rotating away or towards it. It Oh yeah, right. Sorry, because you're not on a ball rotating away from it. We predict that the star is going to traverse that full arc length, that full gamma, that full 27 arc minutes, and that's what's happening. I actually just added another section to the spreadsheet real quick, if you want to take a look, to kind of illustrate that the significance of that. So for Pikes Peak, if we go over here, we have this new section called Central Angle Analysis. Now I'll try and integrate this a bit better and make it look more pleasing or whatever. But for now, we have the relative central angle and the half central angle, so the drop over distance and the distance between observer and peak. Now, the star on a flat Earth would be predicted to traverse pretty much the entire arc length, and here it traverses 25 arc minutes of the arc length. And so, for the observer, in other words, The time it took for that occlusion to occur was beyond what the globe would predict because the sky and the ground are curved together. So half of the work is already done on the globe side. So they would only predict that the star has to drop 13 arc minutes to occlude. So they would never predict the full amount. But then when you see they add refraction back, they add the refraction to compensate for their would-be drop. Well, that offsets the timing to match what flat Earth predicts for the full arc length transit. So they predict 13, we predict, more than that, closer to the full amount. And that's what happens on every single measurement is we're just using rise over run. We're always closer to the full arc length traversed, whereas they have to add in astronomical refraction, and some of them also want to add in terrestrial. So they're trying to get in 3 total corrections, one for drop, one to remove it, and another one just to round it off, I guess.
Well, Alan, if you want to predict for the globe, you have to do it correctly. Now, if you want to minimize the effects of refraction or disregard them, you need to pick a target that is higher in elevation than a mountain 2 degrees above the horizon, which is exactly why I picked planes and balloons, and why my data show that even if you ignore refraction, the globe wins.
So you don't account for any measurement uncertainty when using a moving plane that's changing in elevations and the data you get being a half-second delayed and a 1 second plus or minus. Your target's moving 300 meters plus or minus. So you're never going to get the exact distance or location.
Wrong.
You should have chosen.
I accounted for the uncertainty.
Oh, 1 second, dog. This isn't actually where you start interrupting me and talk over me. We're in the middle of discussing why the globe geometrically predicts an earlier timing. If you want to discuss your data or have a follow-up discussion about it, that'll be at a later time. I don't have time tonight. We're on a time schedule. We got some family events to do in about 15 minutes.
You mean, oh wait, yeah, earlier, sorry.
Yeah, sorry. So I politely ask that you settle down for a minute while QOP and I discuss the why the globe predicts an earlier timing. So we're trying to get that hammered out before we get to other facets. Thank you. Sorry, go ahead, QOP.
I mean, I agree with both of the parts of the model where the flat Earth should have at times an extended sky.
Every time.
Well, it doesn't.
Show me a measurement on here that you think it doesn't, and we could talk about it.
Well, on there, that's circular again. Remember, so your occlusion timing's happening later than stellarium claims. Then stellarium claims doesn't prove your reason for why that happens.
Oh, that's not circular. That's a geometry. We predicted later
No, because of it. You said you changed your prediction.
But it's only off by a couple seconds usually.
No, he's not even talking about that, Lamazing.
Oh, he's not?
We didn't change our prediction. We changed how we talk about it to accurately represent what it is. Because irrespective of us being wrong about it at the beginning, how I was articulating it, doesn't change the fact that it is later and it is earlier, or for the globe. Nothing was changed in terms of how we're doing anything. All that changed is we added the way to convert the angle to time to see what it is, and then we just noticed that it was oh, it's actually reversed in that way. And then there's a specific geometric reason as to why, which is the chord tangent theorem. So it's not that we changed it, it's that we've understood it better, what it actually is, and the actual geometric theorems as to why. So if we make the prediction, right, if we're just talking no refraction, just geometry, the globe always predicts a lower one because it's already lower, because they're comparing it to the observer at the center of Earth. I don't know if you were on when I went over that at the beginning, but when they, when they're like, when they're like, where's the true position at? When we open up stellarium and we turn off refraction, the true position is being derived by comparing it to where it would be seen as an observer at the center of Earth. So it always lowers the angle for them. So hopefully that kind of helps illustrate why. So tonight, though, because like I said, we're getting close on time here. Is everyone getting the reason as to why they predict a lower or an earlier timing versus the later timing. Are there any more questions that we could answer on that?
I'd just like to thank you for your presentations, Alan.
No worries, lad.
So, Alan, you claim that I didn't account for uncertainty, but that's absolutely false. And in fact, these.
Oh, Astronomy Live, you claim that you're talking about your data and we're talking about geometric intersections and why the globes earlier. This isn't where you come and just interrupt and disrupt everything in the middle of the show, buddy. Like I said, we can talk about your data. We can do a planned, scheduled thing, but we're not doing it right now in the middle of this. Helping everyone understand the geometry thing is way more important than going over what you're going over right now.
Well, you chose to mischaracterize what I did, so I had to, set the record straight there.
Cool. You are super welcome to set the record straight when I'm done here. So you can set it straight as long as you want. Go ahead.
Can you give like an average like amount of like how many seconds late the occlusion's happening from what Stellarium claims, and what's like the variance between like the most and least it's off on according to Stellarium?
I could average it out in seconds. I have not done that yet, but I can do that for you between now and next update.
I was just wondering something like really rudimentary just to get an idea of what we're talking about.
Yeah, so to start us off here, Pikes Peak, flat Earth, there's an 11-second difference between what's predicted and what was measured for flat Earth. And then for globe, there's a 1 minute and 3 second difference. So they predicted it, earlier by that amount. And then for an extreme case here, like North Peak, let's see. Excuse me. We have, didn't update. Or did it? For this one, we end up being off by 3 minutes. The globe ends up being off by 5. So that was one of the longer ones.
And note that one is less than 1 degree above the horizon, and Dr. Mike noticed that it falls apart at that point, and he did have a correction to account for that parallax error, as he calls it. That's still a work in progress.
Yeah, I have not got to any of that yet, but that is a potential work in progress. Let's see here. So one that Goose just got recently, let's see, I think it was Plateau Mountain here. So for Plateau Mountain here at 59 kilometers, we end up being, as soon as the time loads, 1 second, we end up being 25 seconds off. Globe ends up being 2 minutes off. It's another one that Goose did. So this one's really interesting. 77 kilometers, elevation angle of 115 on a flat Earth, 54 on a globe for arc minutes, and then the refraction correction basically, adds back their drop over distance, which is expected. But this is one of the rare times when when just the raw rise over run is closer to even the refracted corrected position. So 5 seconds there, 2 minutes there for the globe. And then if they refract up, they can delay it to be only 7 seconds in difference instead of 2. So yeah, it's kind of like within that range. But I can get you specific averaged out stuff if you'd like. I think that'd probably be useful anyway.
Did you see the spreadsheet I showed on my video that you presented?
I can pull it up real quick.
So I showed Edisbilwin Mountain Peak.
Ah, yes.
So
here we go. Yep.
I just thought it was weird that the true and the Celtio method for FE with refraction off was 499, and that was the same as the globe prediction.
Yeah. So check this out. You see how we're off by 145, which is pretty close to what the drop over distance is. Oops. Sorry. They end up being off by double that amount for their raw geometry. The intersection difference comes out to be like a residual over the arc length. So if the arc length is basically however much of that gets traversed plus or minus is going to create the half gamma offset to it, but it's distributing it over the same arc length. So that probably sounds confusing, but it's basically splitting the half gamma over a larger arc length than what is predicted. And so that's why that comes out like that, where we end up with this amount, they end up with double. But the reason for that now, so check this out. When we do the traverse thing, you know how I talked about earlier how we predict that it traverses the full central angle, they predict only half, and then on emergences it gets reversed. So we actually predict the earlier time, and then they would predict the later time for emergences. When we do the star traversed, if we flip the sign here, because it's an emergence, if we flip that, and we flip their hypothetical as well, I think we need to subtract that one. If we flip that, we get exactly, so if you're on the peak, remember the observer, like on a flat earth, the star is going to rise when its true position is above the elevation over the mountain. So the emergence is going to happen with respect to the mountain. There's a 22 arc minute central angle there. When the star, if you move the occlusion back to 117 from the time of occlusion, you'll see that's the arc length that the star traversed to the peak, and that's why they end up in like that snapshots it at that point. So that's where they end up being off by the excess amount, and it splits it between us. So it's not flat. And another thing to note is that the green up here, because we're doing it from the peak to the star, this is a flat baseline. So like, even though the number is close to what they would predict, like geometrically, this baseline comparison couldn't prove Earth curvature. It wouldn't be possible because the baseline's flat. It would, if we were off by actual curvature, it would look more like this, where, let me change it to Pike's Peak test. It would look like this, where we absorb the drop difference as our air, is our elevation air, and they get almost no air. So hopefully that kind of helps clear that aspect of it up. I know that kind of sounds like a lot, but it's a math relationship as to why it ended up that way over that arc length.
So, Alan, if I saw a plane that was, say, 90 kilometers away and the celestial theodolite air was something like 400, 450 meters, but I had a second observer directly under that plane looking up, measuring the altitude of that plane based on its known physical size and the apparent size that it shows. And I verified that the ADS-B uncertainty is what I said, which is more like in the order of about 60 meters in altitude, not 450. How would you explain that?
Yeah, how would you explain not being able to follow simple instructions of we're discussing geometric intersection timings? If you would like to
This
come
is
back and
geometric intersection
if
time.
you would like to come back and discuss your data and the contentions with the elevation and timings of the planes, we could schedule an event for that. We're doing a different thing right now, and you're being very disruptive.
Again, if you want to block me for discussing geometric intersection, that's up to you. But
Yeah, I'm going to go ahead and block you for that real quick, actually, since you can't stop interrupting while we're discussing why the globe has an earlier elevation timing. You're happy to schedule an event next week, or we could work something out and do it at another time. But the limited time that we have tonight is dedicated to this issue right here that's been long standing, long before you and I ever met. So we're going to try and deal with that tonight.
Well, so I mean, clearly optics is changing the amount of delay from stellarium's prediction. So, right, it's not like a exact amount of of delay
Sure.
of the occlusion timing, right? So
Sure.
there's some aspect of optics that's causing it to move around.
I don't disagree with that. It would be hard to quantify exactly how much, but yeah, for sure.
And how can you guys claim like actual like geometrical claims of like what it's actually showing?
Because we can predict it with just using rise over run, and they require 2 additional corrections, one of which is spherically integrated to assume the correctness of their model. So it can't possibly not compensate for any differences. So just using, the rise over run and then following chord tangent theorem, when we check that star's position at that peak, it's never close to the elevation angle that they assert to. And for them to say that, like, oh, it's just the exact amount of refraction required every time is, I mean, they could say that, but they're giving up the geometric argument for the apparent argument. And the geometric argument is a much stronger position to be in. Like, regardless of why there's a timing difference, the fact is they predict an earlier timing. We naturally predict a later timing. They have to correct to our natural late timing.
The more interesting question to ask is, when doesn't it work? And then why? Not that I have an answer, but just those are the things to think about.
When doesn't what work?
When doesn't going to the peak and looking at the intersection differences show the globe, like, when would it show globe proof? Essentially, when does it not work?
When the occlusion is very close to you, which is what my discussion was about, Alan, that if you've got the same angle, the same time of occlusion.
Incorrect, Daza. Your discussion, little did you know it, was about the timing differences for flat Earth versus globe Earth. So using the raw geometrics, do we all agree that the globe would predict the earlier timing for the observer-centric prediction based on how they would compare it to the observer at the center of the Earth? Does everyone on board now?
It's a simple geometric prediction for the globe.
So the answer is yes, Alan. I agree that the globe does have the earlier timings when speaking purely geometrically.
Yeah, and if you were to take all of those timings, so if I was to move my occluding stick along the line of sight to the peak,
Yeah.
the occlusion
Yeah, one
as
second,
predicted by
dog.
the
So
globe model
one
would be
second.
consistent all the way, right?
No. That's what we literally have measurements from peaks showing that it's not consistent to the fucking
The
globe.
globe would
So
consistently match what flat Earth predicts.
so anyway, Daza, let's not pretend like the agreement of the earlier timing for the geometric is insignificant here. This is the gap that needs to be bridged by both sides. So it would be nice if you would articulate instead of just going, yeah, and acting like you're kind of half agreeing. Do you understand why they predict an earlier timing?
No, I don't really understand your model, to be honest, because it doesn't work for everybody at
Okay,
once. So
okay, great. Okay, great. Thank you. That's all I needed to hear. Thank you. Okay, so you have no idea what's going on here. You're calling our model, which we're referencing the celestial sphere, which is how the globe makes their predictions for where the stars should be. You're calling that our model and saying you don't understand it. So when I was saying the globe predicts it earlier because of these reasons, and you just glossed over it and said yeah, and then started to make a completely different argument. You can't do that here. We're trying to get understanding. So if you don't understand why it predicts an earlier timing, it would be nice if you just talked over me while I'm talking. That way it ensures that you hear exactly what I'm saying and we can have a productive conversation. So, dude, you can't fucking be serious. Just stop talking over me, Daza. So, we're going to go over this, the celestial sphere, right? Real quick, so I don't have much time left, but I'm going to leave you guys with this thought. I'll unmute you, Daza, so you're not muted the whole time, but please don't interrupt me when I'm about to land this plane here. Give me 1 second, and then you can go back to pretending to have a conversation. Okay. Calculations of celestial navigation always refer to the geocentric altitude of a body, the altitude measured by a fictitious observer being on the plane of the celestial horizon at the center of Earth, which coincides with the center of the celestial sphere. So they have two spheres, terrestrial sphere, celestial sphere. Celestial sphere has got infinite radius. Terrestrial sphere, they say, has a radius of 3959. They merge these two spheres together. The observer moves from the top here, from the topocentric position, to the geocentric position down here. When they do that to compare where the geocentric altitude of the star is, that lowers the star's position. And that right there is fundamentally why, like that is the core backbone fundamental of why the globe predicts an earlier occlusion timing, because the star is already lowered to the elevation of the mountain that they predict at the horizon. Now, I'm going to, if you have a question about that or whatever, we can go over it real quick, but I am pressed for time.
So aren't the lines in your diagram from the geocentric observer to the topocentric observer parallel? So if we were to draw line C to the body and the observer to the body, those lines are parallel, right? So the angle between the body and the celestial horizon is the same as the angle between the observer and the observer's horizon and the body.
They get that lower elevation by first comparing it to the observer at the center of Earth. Without that comparison, there's no true position for them to even reference. All they have is an apparent position at a specific elevation band. To get this true position, they note the elevation, they subtract how much refraction there is for that elevation. That gives them the angle that the star would be viewed as if it were an observer at the center of the Earth, and it lowers the angle every time.
But if we go back a step, though, back to the pure geometry before we apply refraction, we can move the line from point C to the body directly up the zenith to the observer, and the angle H, which is the angle between the celestial horizon and the body, is the same at the observer's position, right?
Daza, are you saying is the 90 degree going to be 90 degree?
No. Angle H in your figure 1.3 here, we can slide that triangle up the zenith till it hits the observer's position, and the geoidal, is it geoidal horizon? Sorry, it's a bit small on my screen.
Yes, Daza. Yes, yeah. That's what this comparison is, what defines that angle for that guy, because he doesn't see this.
Yeah, so angle H is the same from the center of the Earth as it is for the observer.
Mm-hmm.
Yeah. And then you may need to apply refraction to get the apparent angle.
No. You are grossly confused. You remove refraction to get this angle that you would move up to the observer location.
So we've got two sets of angles. One is the actual geometric
Daza,
angle.
Can you read this out loud real quick?
I can't see it. It's too small.
It's okay. I'll make it super big. Can you just knock this one out for me? This red sentence.
The calculations of the celestial navigation always refer to the geocentric altitude of the body. The altitude measured by a fictitious observer being on a plane of the celestial horizon and at the center of the Earth, which coincides with the center of the celestial sphere.
Okay, so we're not adding refraction.
This angle H, right, is what we're talking about there.
Yeah. We're not adding refraction back to get the apparent. No, but they don't do it off of apparence. It's based off of the true position.
Yeah.
And this true position is defined by this comparison right here. That's why it's lower, always.
Yeah. But then if we slide that triangle,
if you slide this triangle up, it makes that lower angle for the observer. That's it. That's why it's lower.
No, the angle doesn't change. You slide angle H up.
Daza.
Still angle H.
Daza.
Right? Because the body is so far away that the line from the GP to C is parallel at the observer's position as well.
Can you just listen for a second? They don't know what this angle is yet. All they have is an apparent position as observed by a guy up here. Okay? This guy sees it at this angle. He goes, how much refraction is at that angle? Oh, let's say 3 arc minutes. So he subtracts 3 arc minutes from it. That makes it relative to the fictitious observer at the center, lowering the angle. This angle H then becomes his angle. And that is why it's already lower. That's why when we go into stellarium at these times, that's why it's aligned at that earlier time.
So we're talking about 2 different angles. One's the refracted angle and one is the geometric angle, right?
Nope,
So
we're only
this figure
talking
here
about
is
the
geometric.
we're only talking about the geometric angle. We're talking
Okay.
strictly the geometric comparisons and why geometrically the globe makes the earlier prediction. Because the star
so
is
you're saying that
already the star is already lowered, because the star that they're going to be referencing, the angle, is lowered by their correction where they compare it to the fictitious observer down here when they remove refraction.
Yeah, so you're talking about how we establish the star's geometric position, not this process of moving the angle to the observer. So you're talking about how we turned observations into the RA and declination of all of the bodies.
Nope. Talking about why the angle is lower. It's at a higher angle, and then you compare it to where it would be to the center of the Earth, and it becomes a lower angle. Yes or no?
So that
yes
there's
or
nothing
no,
in figure
Daza?
1.3 that will change the angle. Right?
Daza. If you see a star and it's refracted above its true position, and you remove the refraction, its true position would then be lower than its apparent position, right?
But we're talking about the
geometric.
geometric.
Yeah, but no. Just fucking, you're confusing yourself. Just simple yes or no's real quick. So if the apparent position that we see is higher than the true position, and then we remove the refraction, the true position is lower than the apparent position. Yes?
Yes.
I think so, yeah. But this diagram's talking about geometric position.
Jeez, dude, just fucking you. All right, well, you get to this geometric position, Daza, by removing the refraction. Moving the angle up to the observer isn't the relevant part of this. The relevant part of this is that it's always lower than what is optically perceived, right?
Not always, no.
No, sometimes. Okay, dude. All right, all right. QOP, did you have anything you wanted to ask before I wrap up for the night?
Did you ask me?
Yeah. Or ask QOP.
No, that's pretty much all my questions.
All right, cool. Well, if you have any more or whatever, send them my way. We're gonna wrap up for this evening, and then we will be back to go over this again, because I sense that it's not landing somehow. So we'll be back to talk about that at some point. So see you guys on next Monday.